Hey everyone. In the last video, we have seen the limitations that we would face with doing context engineering with all your domain data. And in this video, we're going to see how we can actually overcome that using a technique called Retrieval Augmented Generation. Everything in LabVIEW, right? So just to refresh, in the last demo, what we have seen is I was able to kind of provide an error message, and I was able to kind of get the root cause analysis using the domain context that is provided in the system message. And whenever I provide an error that is not in the domain context, it kind of says, I don't know, right? But now the challenge is I only give three errors here, right? But essentially what I have is I have total of 15 errors in this particular text document. Now, how can I know figure out the right set of error messages that I can put it into the system context based on the potential error that I would receive, right? Essentially, how can I, from all the domain context, how can I zoom in into relevant domain context for the current scenario that I have in hand? The current scenario that I have in the hand is there is a pump failure in a pump 3. How can I find all the domain knowledge that is relevant to the pump 3 failure? Probably all the domain knowledge is probably like pump 1 failure, pump 2, pump 3 failure, right? All these make sense because all these are related to the pump failures. But I don't wanted something like vibration exceeds limit, data log failure, and everything, right? So in the next few minutes, I'm going to talk about a concept called retrieval augmented generation that helps you zoom in and retrieve your relevant domain or context from a big data set and then provide that to LLM so that LLM would be much more efficient, right? So that's what we are going to cover in the next few minutes. So to start with, retrieval augmentation generation has two important steps. Whenever the user provides a question or a scenario, in this case, a pump 3 failure is a question or a scenario. What our AI application will do or should do is it will be orchestrated in a way where we will take the user's scenario or question or whatever it is and try to look into your domain data, the big corpus of domain data that you might have, and then retrieve a specific set of information that is relevant to the user question and then provide the context to the model so the model can perform better. In the last videos, we have actually seen the right side part. I think once you have the context, you can actually provide the context to the LLMs to get the response that you wanted. In this video, we are going to primarily look at the left side. How can I retrieve that particular relevant context from the large set of data that you might have in here actually? So to do that, you have two steps actually. One is you have to vectorize all your knowledge into nodes. Step one, I'll kind of explain what it means. The second one is how can you search and retrieve the relevant nodes from all this vectorized nodes, right? These are the actual two steps. So I'll kind of explain that using LabVIEW. So let me open LabVIEW here. All right, let me close this VI. So first step, you might have a lot of data. First step is to vectorize these informations, right? So similar to the GPT-4o model, which we have seen, which does a text-to-text conversion, we have models that does text-to-vector conversion. A vector is nothing but a numerical representation of the text in several dimensions, actually. I'll do a separate video just to kind of talk a bit more about the vectors, how the vectors are created, what does embedding mean. But for now, for the sake of this particular video, you can just remember a vector is nothing but a numerical representation of the text that is, the AI systems can or such systems can understand much better. So we have a model called embedding models, similar to the text-to-text generation models. The way you call it is very similar to how you do a text-to-text generation. You instantiate a embedding model, provide what is the model name and what's the key. You do run. and then you do a destroy. But while running, you provide the input as a text message. So I have just created a text message. Text message is nothing but from the notepad that I have shown you in the previous video where I had all the list of issues. Each element in this array is list of an issue and what could be the possible reason and how to fix them. And that's an input message, right? It's a text message, and it provides a vector as an output, right? So when I run this VI, it takes this text messages and converts into these vectors and provides me the vectors that I can kind of see. Let's give it a few seconds. All right, now it has gender, and you can now see this, right? So for each element in the left side, you will see an element in the array in the right side, and it has bunch of vectors. Now these numbers, you can't understand any of these numbers. These numbers are just based on the embedding model. It's just a representation of the steps on the left side. Now, um, there are search algorithms that can actually look at these numbers and then find what are all elements that are closer to each other, right? What are all information that are relevant, right? So to start with, first what we wanted to do is we want to kind of feed all these vectors into a database, so that we can actually search and retrieve some relevant information or relevant nodes from the particular database. So database that we would you be using typically to store vectors are called vector databases. There are a lot of vector databases out there. There are Pinecones, quadrants. There is also a lot of like a local file-based vector databases. Uh, in LLM libraries, we have support for quadrant by default. So let me actually open the example where we actually vectorize the information and store it in the quadrant database. So it's an extension to the VA that we have seen, where we take we use the embedding model and the input messages, and we take the output, I mean create vectors, and the output vectors is now stored into a vector database. Again, LLM libraries have APIs to access the vector database. Essentially, we have an API to instantiate a vector database, um, create a collection. Collection is nothing but uh, you can kind of create like a namespace or a space within which all these vectors are stored. Once you create a collection, you actually store the vectors, and then you actually destroy it. Now, let me actually open a vector database so I can actually show things getting stored in the vector database. I think I have created one already, so let me go ahead and delete that. Okay, so I'm going to create a collection called basic vector search demo. So once I run it, and this VI, it's going to create the vectors and store it in the vector database. So you would be seeing seeing the information getting stored in this vector database. This is nothing but a web view for the vector database where you can view the collections and entities under the collection. So I think this is done. So if I refresh it, I should see the collection pop up here. Great. Like I said, it has 15 entities because I took all the 15 errors and created the element for each of the one. So you can kind of see, jump into the collection. You can see, okay, here are the each error messages in the vector database. Now you can actually visualize the text as well as the vectors. So you can visualize the vector using it has something called visualize and graphs, where you can view the vector. So each of the dots is a vector. Uh, this is this is how the vectors are represented. I mean, if you can imagine, like if you have an XY graph, you have a point which says, okay, that point is in what X and what Y. This is more like a 512 dimensional. It's not two-dimensional or three-dimensional. It's 512 dimensional uh, vectors. So you can, like in the human mind, it's tough to visualize how does a 512 dimensional thing looks like. But they're trying to kind of put together in some kind of form factor here. Ideally, how it looks, how it works is all the vectors that have similar meaning sits together or sits close to each other in this 512 dimension. So, for example, I have errors related to pumps. All those sits together. If I have errors related to motors, or I have error related to some like boilers or whatnot, these are all grouped together. in this 5 and 12 dimensional thing. So whenever I have a question about, say, pump, um, we actually take that particular question, convert that into a vectors and see what all vectors that's close to what I'm looking for. And when I retrieve those informations, those are going to be mostly like relevant information. Right? So that is what we are going to apply here. So what you have seen so far with the LabVIEW code that I have shown is we took all the error information, converted into vectors using the embedding model, and stored them into the vector database. Like I showed in the slides, the next step is we're going to search and pull the relevant nodes from here, right? So let me kind of explain that using the LabVIEW code called retrieve nodes. What this retrieve node does is it's simple. We we are going to give in an error information or some message as an input. It's going to look into the database and find what are all the potential errors that is relevant to what I have provided. For example, say I provided some information like pump issues. What it does is it takes the pump issues as an input, um, creates an embedding out of it. Similar thing, open an embedding model instance, give this information, create a vector, and use this vector in our vector database to do a search and retrieve top three probably closest entities to this particular vector and provide that as an output, right? It's a very simple code. Again, uh, 5 APIs to do LLM works, and then 3 APIs to do a search from the vector database. Now, when I say pump issue and I run it, it kind of provides me 3 issues that are relevant to the pump. It says pump 2 overcurrent detected, unexpected pressure drop detected, and pump 1 failed to start. Now, if I provide something like pressure issues, it provides me top 3 issues that are relevant to pressure. So it kind of comes up with saying unexpected pressure drop detected, tank over pressure condition, pressure sensor out of range, right? Again, it doesn't mean you have to always get top 3. You can even get like top 5 if you wanted, top 10. It's up to that's up to you to kind of configure. Essentially, you are deciding how much nodes or how much context, relevant context that you want to extract from your whole database and provide that to an LLM. Now I provided 5 relevant nodes as a request, and it provided me 5 elements, right? So this is a way in which, given you have a very huge domain context, you can zoom into what are all the relevant information that you wanted, and you can feed only those to LLM inference system, right? So um, this is exactly called RAG, right? Retrieval Augmented Generation. So far what we have seen in this video is I showed you how we can take all your data and vectorize and store it into a database. And then for a given scenario, how you can retrieve segments of data that you are relevant, that you wanted, right? Um, Quick thing to kind of close this video. The last part is how you can now augment that particular information to have LLM summarize it. So essentially, I just combined the VA that you showed in the just now, which is retrieving the top 3 nodes and then providing that as a context to the LLM. So it provides me the right response, right? For example, if I can say a system message is find the root cause, and I'll say I have 8903 pump 3 issue. Now when I run it, it's going to find the relevant error message for 8903, and then it's going to use that. It found out 8902, 8903, and 8901, and it's going to use that as a context and generate the response. And it kind of provided me the final response, right? So this is a kind of a quick demo on how we can use retrieval augmented generation in LabVIEW purely developed. All right. Thanks so much.